Today we'll discuss ISI's 2023 UGB paper, and the first question is determine all integers n greater than 1 such that every power of n has an odd number of digits. Now the first concept that we need to learn here is how to find number of digits for any number n. So if we have a number n, then number of digits, it is given by 1 plus greatest integral function of log n base 10. Now we want every power of n to be an odd number. So if every power is an odd number, so this n itself should have odd number of digits, and it will have odd number of digits if this log 10 base n, it is an even number. So it is an even integer. So we can write this log 10 base n, it should be some 2k plus its fractional part f. So where this k, again it is an integer, and this f, it is a fractional part, so its value will lie between 0 and 1. Now we want every power of n to have an odd number of digits. So if we take any power of n, say n to the power r, we can write this as log 10 n to the power r, and it will be 2kr plus r into f, and number of digits in n to the power r, it will be 1 plus greatest in function of log n to the power r base 10. Now again, it should be an odd number. It will be odd if this is even. Now in this, we already know this 2kr, it is even. Now what about this rf? Now the problem is, if we multiply r with f, it is possible that you'll get this rf such that it lie between 1 and 2, or in general this rf, it may lie between some 2m minus 1 and 2m. In this case, when we take this greatest integral function, then this part it will be even, but this rf, it may give us odd result. So depending on the value of r, it will give us odd result or even result. But the condition here is it should always be an odd number, and always be an odd number if it is even, and it is even if and only if this r into f part, which is making it dicey, it should not be there. So that means it is possible if and only if f is 0. So from here we have derived the condition that this rth power of n, it will have odd number of digits if and only if its fractional part is 0. And when f is 0, we can simply write log n base 10 as 2k, or n is simply 10 to the power 2k. So a number whose every power has an odd number of digits is of the form 10 to the power 2k. And that is the answer to this question. Now in the second question, it says if a0 is 1 by 2 and an is defined inductively by an equals under root 1 plus an minus 1 by 2, then show that an equals cos theta n for some theta n lying between 0 and pi by 2, and we need to determine theta n. Now we are given a0, which is 1 by 2, which is cos 60, and that is cos pi by 3. And let us say this is cos theta. So theta here is pi by 3. Now if we use this relation, then we can write a1 as under root of 1 plus cos theta whole divided by 2. Now this is under root of, and 1 plus, we can write this as 2 cos square theta by 2 minus 1 upon 2. Now this 1 and 1 will cancel, this 2 will cancel, we'll get this as mod cos theta by 2, and since theta by 2, it lies between 0 and pi by 2, we'll get a positive value. So we can simply write this a1 as cos theta by 2. Now, if we replace A1 in this formula, we'll get A2. So this A2 will be under root of 1 plus cos theta by 2 whole divided by 2. It is the same expression. So what it will do is, it will give us this result cos half of this given angle. So from here we'll get this as cos theta upon 2 square. So A1 is 2 to the power 1, A2 is 2 square. So if we continue like this, we can write this AN as cos theta upon 2 to the power n, which is of the form some cos theta n, where this theta n, it is theta upon 2 to the power n, and theta is pi by 3. So it will be this pi by 3 into 2 to the power n, and clearly this value, it lies between 0 and pi by 2. So that's our first part. Now for the second part, we have to find this limit. So we need to find this limit n tends to infinite 4 to the power n 1 minus an now this is limit n tends to infinite. Now first we are going to write 1 minus an, which is 1 minus cos theta upon 2 to the power n divided by, and we can write this as 1 upon 4 to the power n, which is actually 1 upon 2 to the power n whole square. Now as n tends to infinite, theta upon 2 to the power n, it tends to 0. So we can make it a standard limit. So what we'll do is, we'll multiply and divide everything with theta square. Now this is 1 minus cos x upon x square when x tends to 0, which is standard limit, whose value is 1 by 2. So this limit will be 1 by 2 theta square, and theta is pi by 3. So this value will be pi square by 18. So answer to this limit is pi square by 18. Now in this question number 3, we are given this triangle ABC, and it says consider points D and E on AC and AB respectively, and assume that they do not coincide with any of the vertices ABC if the segments BD and CE, they intersect at F. Consider the areas W, X, Y, and Z of quadrilateral AEFD, triangles BEF, BFC, CDF respectively. Then we need to prove these two results. Now what we'll do is, we'll join this A with F, and suppose this area W, it is divided in two parts, W1, and this other part is W2. So basically our W is W1 plus W2. Now we can write this ratio AD upon DC, it will be equal to area of triangle ABD upon area of triangle CBD. Since they'll have the same line, from B they'll have same perpendicular distance, the ratio of their areas will be proportional to the ratio of their bases. Now this ABD, it is X plus W1 plus W2 upon CBD is Y plus Z. Now we can also do this thing AD upon DC for these two triangles, AFD and CFD. So this ratio will also be equal to ratio of areas of triangle AFD upon area of triangle CFD. Now area of triangle AFD, it is W2, and area of triangle CFD is Z. Now using the properties of ratio and proportion, we can write AD upon DC, it will be equal to area of triangle ABD minus area of triangle AFB upon area of triangle CBD minus area of triangle CFD. So basically it will be equal to x plus W1 plus W2 minus W2. So there will be x plus W1 upon, and here it will be y plus z minus z. So there will be simply y. And if we equate these two, we can write x plus W1 upon y, it is equal to W2 upon z, or we can simply write minus ZW1 plus YW2, it is equal to XZ, and that's our first result. Now we are going to repeat this entire exercise for these two sides, AE and BE. So we can write AE upon BE, and that is equal to area of this triangle AEC, and this AEC will be Z plus W1 plus W2 upon this area, which is x plus y, and it is also equal to ratio of this area AFE and BFE, which is W1 by x. And again, using properties of ratio, we can subtract these two. So it is equal to Z plus W2 upon y. Now we are going to take these two and cross multiply them. So from here we can write YW1 minus XW2, and that is equal to XZ, and that's your second result. So now we have two linear equations in W1 and W2. Now we're going to solve them. So we can write W1, W2, and this is minus 1. Now this is B1, B2. So this is Y minus X, XZ, XZ. Now this is XZ, XZ, minus Z, Y. This is minus Z, Y, Y, and minus X. So it is W upon XZ, and this is X plus Y, and this is W2 upon XZ, Y plus Z, and here it will be minus 1 upon XZ minus Y square. So we'll take this minus down, so it will be 1 upon Y square minus XZ. So from here we can write W1 as XZ X plus Y upon Y square minus XZ, and W2 as XZ upon Y plus Z divided by Y square minus XZ. Now first we'll solve this second question, which is determine W in terms of X, Y and Z. Now W is basically W1 plus W2. So we can simply write W as W1 plus W2, and if we add these two, Y square minus XZ, that's the denominator, XZ will be common, and here it is X plus Y plus Z. So there will be X plus 2Y plus Z, and that's your result B. Now since this W, it is area of quadrilateral, it should be greater than 0. Now X, Y and Z, they are all areas, they are all positive. That means this denominator, it must also be greater than 0. So from here we can say this Y square minus XZ, it should be greater than 0. That is Y square should be greater than X into Z, and that's your first part. So we have solved both the parts. So this first part is Y square is greater than XZ, and the second part is determine W in terms of X, Y and Z. Now here the fourth question is, let n1, n2, n51 be distinct natural numbers, each of which has exactly 2023 positive integer factors. So any ni, it will have 2023 positive integer factors. Assume that no prime larger than 11 divides any of these ni's. Show that there must be some perfect cube amongst ni's. You may use the fact that 2023 is 7 into 17 into 17. Now, since there is no prime greater than 11 which divides this number, so this ni, it can be expressed as 2 to the power a into 3 to the power b into 5 to the power c, 7 to the power d into 11 to the power e. Now in this case, number of factors, it is given by a plus 1 into b plus 1 into c plus 1 into d plus 1 into e plus 1, and that is equal to 2023. Or we can write this as a plus 1, b plus 1, c plus 1, d plus 1, e plus 1. It will be equal to 7 into 17 into 17. Now we have taken 51 such numbers. So here what we are going to do is, we are going to count how many numbers ni's are possible so that they have 2023 positive integer factors and yet they are not a perfect cube. So one case is, if we want to take these 7, 17 and 17 separately. So in this case, one of the number will be 6 and then 16 and 16, which doesn't make a cube. So first case is when we have 7, 17 and 17. Now are these 5? One of them must be 7 and 2 of them must be 17. So anyone we can choose in 5c1 ways, and then from the remaining 4 we have to choose any 2. It can be done 4c2. So it will be this 5, 13. So if we take 7, 17 and 17, in that case there will be 30 such numbers which have total 2023 positive integer factors and yet they are not a cube of a number. Now if we take this second possibility, and the second possibility is if we multiply 7 with 17, then in that case it will be 119 into 17. Now this a minus 1, there will be 118, and here will be the 16, so which again does not make a cube. So here we'll just need to choose 2 factors for these 2 numbers, and it can be done in 5c2 into factorial 2 ways, and there will be 20 ways. So here also we'll get 2023 positive integer factors and yet there will be no cube. Now our cases are done, but still we'll discuss some possibilities. If we multiply all of them, then it is 2023. Here in this case, this a will be 2022, which is divisible by 3, which is a cube. So we discard this possibility where we multiply all these 3, and another possibility is if we multiply 7 into and then 17 square. Now 17 square is 289. Now this is 6 and this is 288, which again is 18, and in this case also it will be a cube. So this number, it will give you 2023 positive integral factors and yet it will not be a cube only in these 2 cases, and if we add these 2 cases then it gives us 50 numbers. So there are at most 50 numbers whose positive integral factors are 2023 and yet they are not a cube of any number. But here we are given 51 distinct natural numbers. So that means at least one of ni will be a perfect cube, and this is what we need to prove in this question. Now here it says there is a rectangular plot of size 1 cross n, and this has to be covered by 3 type of tiles: red, blue and black. Now red tiles, they are the size 1 cross 1. So we have red tiles whose dimensions are 1 cross 1. And then we have blue tiles. They are also 1 cross 1. And then we have black tiles whose dimensions are 1 cross 2. So we have black tiles whose dimensions are 1 cross 2. Now Tn denotes number of ways in which we can cover this plot of size 1 cross n using these tiles. Now first question is, prove that t2n plus 1 equals tn into tn minus 1 plus tn plus 1. So now for this first case we have this plot of dimension 1 into 2n plus 1. So here we have this plot dimension of 1 cross 2n plus 1. Now let us break it in tiles of 1 cross 1. So we'll continue. Now suppose this is 1, 2, 3 and this is n. This is n plus 1 and this is 2n plus 1. Now let us bifurcate this in 2 parts. So let this line, it divides this plot in 2 parts, where we have this first part where we have 1 cross n, and this second part where we have 1 cross n plus 1 dimensional plot. Now we need to find total number of ways in which we can arrange the tiles. Now we need to find this t 2n plus 1. Now one way of doing it is we can arrange tiles in this 1 cross n plot in tn ways into and remaining n plus 1 in tn plus 1 ways. So this is one of the ways of tiling this plot. Now in this plot we have assumed these 2 portions, they are separate entities. Now there is a second case possible in this where we have this black tile in n and n plus 1 position. So here if they are not disconnected and we have this 1 cross 2 tile here, then on the left hand side we have n minus 1 tiling space, and on the right hand side we have n tiling space. Now this plot of n minus 1 dimension, it can be tiled in tn minus 1 ways, and this plot of dimension n can be done in tn ways. So this t2n plus 1, it is tn into tn minus 1 plus tn plus 1, which is what we need to prove in this question for all n greater than 1. So in this first part, basically there were 2 cases. This first case where we have taken these 2 parts separately, where we have n on the left and n plus 1 on the right, and then this second case where we have this 1 cross 2 tile. In that case we have n minus 1 tiles on the left and n tiles on the right, and these 2 cases, they gave us total number of ways of tiling this 2n plus 1 plot, and which gives us this formula, which is t2n plus 1 equals tn into tn minus 1 plus tn plus 1 for n greater than 1. Now the second part is prove that tn is equal to this summation d greater than or equal to 0 n minus d cd 2 to the power n minus 2d for all n greater than 0. Now for the second part, we have this plot of size 1 cross n, and let D be number of black tiles that we have used. Now since we are using D black tiles, so these black tiles, they are actually going to cover 2D 1 cross 1 blocks. So then we are left with n minus 2D 1 cross 1 blocks, which are to be filled with either red or blue. So what we have here is, here we have D tiles which are black, whose dimensions are 1 cross 2, and we have n minus 2D tiles which are of the dimension 1 cross 1, which are either blue or red. So now we have D 1 cross 2 black tiles and n minus 2D 1 cross 1 tiles, and we have to arrange them in a row, and it can be done in, now total number of tiles is n minus 2D plus D, which is n minus D, and let's choose D tiles for these black ones, so it can be done in n minus D C D ways into, now for these remaining n minus 2D tiles we have two choices, either we can put a blue tile or we can put a red tile. So for each tile we have two choices, so here this Tn, it will be 2 into 2 into 2 n minus 2D times, so it will be 2 to the power n minus 2D. So this Tn will be all the possibilities across all the possible values of D. So this Tn is summation D greater than or equal to 0 n minus D CD 2 to the power n minus 2D, which is what we need to prove in this question. Now the sixth question is, we are given the sequence of real numbers defined as U1, it is 1, and UN plus 1, it is UN plus 1 upon UN for all n greater than or equal to 1. Now if we find U2, U2 is going to be 1 plus 1, it will be this 2. U3, it will be 2 plus 1 by 2, 2.5. So any UI, it will always be greater than or equal to 2 when I is greater than or equal to 2. Because we are adding something to UN and it is clearly an increasing function. Now what we are going to do is, we are going to write this as UN plus 1 square will be UN square plus 1 upon UN square plus 2, or UN plus 1 square minus UN square will be equal to 2 plus 1 upon UN square. And this is the iterative relation we are going to use for our telescopic summation. Since we need UN, we are not going to start with n plus 1, we have to start with UN. So we can write UN square minus UN minus 1 square will be 2 plus 1 upon UN minus 1 square. Next one will be UN minus 1 square minus UN minus 2 square, and there will be 2 plus 1 upon UN minus 2 square, and will continue up to U2 square minus UN square, and there will be 2 plus 1 upon U1 square. Now if we add all of them, then these successive terms, they'll cancel. So we can write UN square minus U1 square, and here this is 2 plus 2 plus 2, and it is from 1 to n minus 1, n minus 1 times. So there will be 2 n minus 1, and plus this is 1 upon U1 square plus 1 upon U2 square up to 1 upon UN minus 1 square. Now U1 is 1, so this is 1, so we can write UN square minus 1, and here will be this 2n minus 2 plus, now this U1 square again will be this 1, and this u2 square, u3 square and un minus 1 square, we know that any ui is greater than 2 when I is greater than equal to 2. So 1 upon ui will be less than or equal to 1 upon 2, or 1 upon ui square will be less than or equal to 1 by 4 for any I greater than or equal to 2. So for all these terms from 2 to n minus 1, we can write this summation I varies from 2 to n minus 1, 1 upon ui square. It will be less than or equal to, now this is 2n minus 2 plus 1 and plus, now this is 1 by 4, 1 by 4, 1 by 4, n minus 2 times. So it will be this n minus 2 by 4. So we'll take this one on the right hand side. So this 1, 1 and 2 will cancel. So we can write un square will be less than or equal to, now this is 2n plus n minus 2 by 4, or we can write un square is less than, now this is 9n minus 2 by 4. Now this 9n minus 2 by 4 will be less than 9n by 4. If we take square root both sides, we can write this un, it will be less than 3 by 2 under root n, and which is what we need to prove in this question. Now in question number 7, it says let n greater than or equal to 1 be an integer. We need to prove that x to the power n plus y to the power n plus z to the power n can be written as a polynomial with integer coefficients in the variables alpha, beta and gamma, where alpha is x plus y plus z, beta is xy plus yz plus zx, and gamma is xyz. Now we need to prove that it is possible to write x to the power n, y to the power n and z to the power n as a polynomial with integral coefficients in these variables alpha, beta and gamma. Now let us start with, say, p0, and p0 is x to the power 0 plus y to the power 0 plus z to the power 0, and this is basically 3. Now p1 is x plus y plus z. Now this basically is alpha. So this p1, it again is a polynomial function with the integral coefficients in the variable alpha, beta, gamma. Now if we write p2, p2 is x square plus y square plus z square. Now this is x plus y plus z whole square minus 2 xy, yz and zx. Now this is alpha square minus 2 beta, which again is a polynomial function in alpha, beta with integral coefficients. Now if we write p3, so it will be this x cube plus y cube plus z cube, and what we'll do is we'll write x cube, y cube, z cube minus 3xyz. We'll take minus 3xyz on the right hand side. So we'll write this as x plus y plus z into x square plus y square plus z square minus xy minus yz minus zx plus 3xyz. Now this x plus y plus z, it is alpha. Now x square minus yz is alpha square minus 2 beta. And here xy, yz, zx, it is beta and plus 3. And xyz, it is nothing but gamma. Now we can write this p3 as alpha into alpha square minus 2 beta minus beta into alpha plus gamma into 3. So this p3, it will be alpha. Now this is p2 minus beta. Alpha is p1 and plus gamma, this is P naught. And we can clearly see P0, P1, P2, P3, they are all polynomial functions with integral coefficients in the variables alpha, beta and gamma. So using induction, we'll say P0, P1, P2, Pn minus 1, they are all polynomials with integral coefficients in the variable alpha, beta and gamma. So we can write Pn, which is x to the power n plus y to the power n plus z to the power n. It will be alpha Pn minus 1 minus beta Pn minus 2 plus gamma Pn minus 3. Now we have alpha, beta, gamma, and all of these are polynomials with integral coefficient. That means this Pn will be a polynomial with integer coefficients in the variables alpha, beta and gamma. And if you want, you can prove this part yourself, and you can prove it starting from here. So we can start with alpha Pn minus 1, and alpha is x plus y plus z, and Pn minus 1 is x to the power n minus 1, y to the power n minus 1, z to the power n minus 1. If you multiply these three, you'll get Pn, and you'll get these two other terms. It is fairly simple, but it will require some calculation on your part. So that's our first part. Now we'll come to this part B, where we are given this Gn, which is x to the power n sin Na plus y to the power n sin Nb plus z to the power n sin Nc, where x, y, z, a, b, c are real numbers such that a plus b plus c, it is an integral multiple of pi. Using a or otherwise, show that if g1 equals g2 equals 0, then gn equals 0 for all positive integers n. Now what we'll do is, rather than taking this gn, we are going to take some zn, and this is x to the power n e to the power iota na plus y to the power n e to the power iota nb plus z to the power n e to the power iota nc, and this gn is nothing but it is imaginary part of zn. So here what we're going to do is, we're going to let three separate variables. Let x dash is x e to the power ia, y dash is y e to the power iota b, and z dash is z e to the power iota c. Now we multiply these three, we can write x dash, y dash, z dash, it will be equal to x, y, z e to the power iota a plus b plus c, which is n pi. So this is cos n pi plus iota sin n pi. So sin n pi is 0, so it will be plus or minus x, y, z. So this x dash, y dash, z dash, it is a real number. It belongs to R. Now if we take Z1 is x e to the power iota a plus y e to the power iota b plus z e to the power iota c. Now it says g1 equals 0. That means its imaginary part is 0. So this z1, it belongs to R. So this z1 is x1 dash, y1 dash plus z1 dash, and it is a real number. z2 is x1 dash square plus y1 dash square plus z1 dash square will be x1 dash plus y1 dash plus z1 dash whole square plus 2 times x dash y dash z dash plus z dash x dash. Now it is also real. Now x dash plus y dash plus z dash, this is real. So that means x dash y dash z dash and z dash x dash, it is also real. So now we have x dash plus y dash plus z dash, which are real. We also have x dash y dash plus y dash z dash plus z dash x dash, which are real. And we also have x dash y dash and z dash, which is also real number. And suppose this is our alpha dash, beta dash and gamma dash. Now using the first part, we can write any z to the power n. It can be expressed as a polynomial in alpha dash, beta dash and gamma dash with integer coefficients. And since alpha dash, beta dash, gamma dash, they are real numbers, so that means this z to the power n, it will be a real number, implying that Gn, it will be 0 for any value of n, and which is what we need to prove in the second part. Now coming to this last question, we are given a function f which is defined on 0 to 1 to r, and it is a continuous function which is differentiable on 0 to 1. Now prove that either f is a linear function or there exists t in the interval 0 to 1 such that f1 minus f0 is less than f dash t. So let us draw the axis. Now this function, it is defined between 0 and 1. Now without loss of generality, let us assume f0 is less than or equal to f1. So let us say this is f0 and this point is f1. Now we join these 2 points using a straight line and say this line is L. Since it is a continuous function, so one of the possibility is it could be this straight line which passes through these 2 points 0 f0, which is this, say this point A, and this other point B, which is 1 comma f1. And we can always draw this straight line L, and we can also write equation of this straight line will be y minus f0 equals f1 minus f0 upon 1 minus 0 into x minus 0, which is y equals f1 minus f0 x plus f0, which is a linear function. Linear function of the form y equals ax plus b. So it could be either a straight line from a to b, which is a linear function, or it could be any other function. And if it is any other function, then let us say there is some point C on this curve, and I'm not drawing this entire curve, I'm just drawing a part of it, and I could have drawn it either upwards or downwards, it doesn't matter. So there is this point C lying between 0 and 1, and suppose whose x coordinate is C and y coordinate is FC. So this point C, its coordinates are C comma FC. Now if we join A with C and B with C, then we have 2 slopes here, slopes of AC and slopes of BC. Now one of these slopes, it is less than L, and the other slope will be greater than L. So that means slope of this line L will always lie between slope of AC and slope of BC. Now in this case, slope of AC is less than slope of L and slope of BC is greater than slope of L. So we can write slope of L, it is less than slope of BC. Now slope of this line, it is y2 minus y1. So it will be this f1 minus f0 upon 1 minus 0. So we can write slope of BC, it will be greater than slope of this line, which is f1 minus f0. Now slope of BC, it is average slope between B and C. So using Lagrange's mean value theorem, in this interval between C and 1, we can say there exists a T in the interval C to 1 and which again lies between 0 to 1 such that f dash t is equal to slope of BC and slope of BC is greater than f1 minus f0. So from here we can say there exists a point T in the interval 0 to 1 such that f dash t is greater than f1 minus f0. Now here we have taken this interval between C and 1 because we have taken this point C below the line L. If we would have taken this point C above this line L, then we would have taken this interval from 0 to C. And this f1 minus f0, we are assuming f1 is greater than f0. And from here we can clearly write mod of f dash t is greater than mod of f1 minus f0. And we are taking this mod sign because we have assumed f1 is greater than f0. If you want, you can take the two cases separately. When f1 is greater than f0 and second case where f1 is less than f0. Whichever way, you'll get the same result. And this is how we solve such questions.